Okay, this video is going to focus exclusively on washers, and I want to kind of take you through the general theory of washers first, and then I'll do 6 different examples. So washers are useful and really necessary when we're going to take an area. So let's take this area right here, so this dark area, and let's revolve it around this axis. Okay, and you can kind of imagine what shape you're going to get. So what would happen if you revolved this line over this axis? Okay, so we just take it step by step here. If we just take this line and revolve it around this axis, well, we just get a straight cylinder. Okay, we get a cylinder, right? Whip this line around, everything enclosed would be a cylinder. Okay, if we take this line and we whip it around this axis, we get a cone. Well, if you take this area and whip it around, well, you get this cylinder minus a cone. Now again, this shape is really hard to imagine, but it's not really that bad if you just take this cylinder and just trying to remove a cone from it. So there's my cylinder. And then take this cone and rip it out. And you're kind of left with this shaded part that obviously goes all the way around, right? It's like this weird dog bowl shape where the sides would go, really steep down. Okay? And so how would you figure it out? Well, the washer formula I don't actually like very much, even though everyone uses it. If you looked it up, this is what it's going to say. Washers are going to be the integral of pi times r squared minus r squared dx or dy. It kind of depends on what orientation you're looking at. But really, if you take this, and you see how a washer gets created, or this hole gets created because there's an area that's not part of the area we want to revolve, that's adjacent to the axis, unlike the previous when we did discs. Right? You're going to revolve this, and there's going to be this big gap here. Again, it's called a washer, and again, later. But if you haven't, put together something at a hardware store, right? That's what a washer kind of looks like. And what we would do is we'd sum up this shape using washers. Okay, but really, the shape, the volume, should be the integral of pi r squared dx, which would give you the cylinder, minus the integral of pi r squared dx. Okay, big R would just be this. Big R. Little r would just be this. And so this is the volume of the cylinder, this is the volume of the cone, and subtract, and you get this. Now, they play some kind of trick and they say, well, this and this are the same thing. This is the formula that I'm going to use the whole time. That's the formula you're going to see in a textbook as well. They're not going to do them as separate volumes and subtract. They're just going to put them together. And on the picture, what you're going to do is to find big R, you're going to go from the axis to the farther away curve. That distance is big R. And then the axis to the short curve, that's going to be, so that's big R, and that's going to be little r the whole time. And that's the picture I'm going to draw every single time. I'm going to draw big R and little r. I'm going to find the equations for them, and then I'm going to use this formula. And again, if you think about a washer here, why they say washers, and again, I'm just going to just barely attempt to draw one of these. If you take this, and you take this curve, and you whip it around, okay, you're going to get something like that. And you take that same outer curve and whip it around, you're going to get something like that. And so when you think of this, that's the area you get. It looks like a washer, and you're going to sum up all those washers. That washer there is kind of thick. The washer up here will be super thin, because rotating that curve would give you this. Rotating the inside curve would give you something really close to it, and you'd be left with almost nothing. But look over here, you're left with almost nothing towards the end, and you have a thicker washer here and then a super thick washer there, right? This curve, and then you subtract this little bitty baby thing right there. When you add all those things up, you can kind of see the cone is starting to form by that inner circle. Again, think of all of these blues are the inner part inner part washer, and then this, all of these are the outer part of the washer. I know I've just completely jacked this up now, but you can see better visuals online if you want. This is the formula. I'm going to use it. I would prefer that you understand that this is where it comes from, but this is the useful formula that we're going to use on the examples. Okay? So, all right, let's do some washers. And I'm going to show you 6 different examples. I'm not going to change the curve at all because the curves don't matter. I can pick any functions I want. I just picked 4x, which is the line, and then y equals x cubed, which is the cubic function. They are going to meet at this point, 2, 8. So we always know that it's 2, 8, 2, 8, 2, 8 on all of those. And on this side, I'm going to revolve in a way that I'm going to stay with x's, and over here I'm going to then use y's. Okay, so this first one, let's just revolve around the x-axis. Okay, so if I revolve this shape around the x-axis, I'm not going to try to draw any of these, but you're going to take this and you're going to whip it around this way. So it's this just weird shape. It's this donut that's thicker here, and I don't even know what kind of shape it is, but visually it doesn't matter. At this point, you have to know how to do the questions. So we know we need washers because there's a gap between the area and our axis. This gap right here is going to cause a hole in our three-dimensional object. So what you need to do is just start at the axis, draw a big R, and draw a little r. That distance is big R. That distance is little r. Again, if you wanted to, you could try to draw one of these washers, and then the little one would go like this. And again, that picture's not going to be very good. I suggest not drawing that. All I would do is draw capital R and little r, and then think about the formula. Again, writing it down again. You're accumulating all of these. Really, you're doing a big volume minus a little volume. And again, it's going to be dx over here and dy over here. And so what we want to do here is the volume here is the accumulation of pi. And then what is big R? Big R was from your axis to the top curve. So that's 4x squared minus little r. Little r was this distance, which is x cubed squared. And the thickness of each washer is dx. When you do that, these numbers will be pretty big. 512 over 21 pi. That's your volume. Okay? All right, let's change it. So instead of the x-axis, let's drop it some. Let's put it down here. Okay, let's put it at y equals -3. I'm not going to draw any more of these washers because it's kind of just a disaster most of the time. So I'm just going to take and go from my axis up to the outside curve. That's big R. That's little r. There's big R. There's little r. And then I know that the volume then is this. I'm summing up. Oh, I didn't even put the bounds on here. What are the bounds? Well, it's x with x's. So I have to have x bounds. So I'm going 0 to 2. Sorry about that. 0 to 2. I'm still stacking the same number of kind of washers from 0 to 2. The big R and little r have just changed. They're just bigger washers now because I've changed this axis, right? I moved the axis away from my area, so it's just a bigger shape. The shape is generally the same idea. So it's pi. And now what's big R? Well, this distance from here to here is 4x, and this distance is just 3. So then big R is 4x plus 3 squared minus this distance is x cubed plus another 3. So I've just increased both of their radius by 3. And again, just as a reminder, if you don't like this whole plus 3 and you don't want to visualize it, you can always, and I mean always, take the top curve minus the bottom curve to find this difference. I mean, it literally is what subtraction does, right? 4x minus a -3 gives you 4x plus 3. X cubed minus a -3 gives you this. And when you type this out, you're going to get 1016 over 21 pi. Okay, again, the setup's the way more important thing. Okay, so we put the axis here, we put the axis here. You know what? Let's put it up top. Let's make the axis y equals to 10. Do the same procedure. Again, if you take this shape and you rotate it around that line, there's going to be this massive hole in here. So you know you're going to need washers. go from your axis to the furthest curve, that's big R, and then go to the close curve, that's little r. You know the volume is the integral from 0 to 2. You're still stacking them from 0 to 2, right? Your washers are still moving horizontally, pi, and then what's big R? Big R is from here to here. Well, from here all the way to the axis, well, that's 10. From the axis to here is x cubed. So this distance is 10 minus x cubed. That's big R squared minus little r. Little r is from here to here. Well, this is 4x. This is 10. So then this must be 10 minus 4x. And I would just remind you, all I'm doing is top minus bottom. Again, it doesn't matter whether the axis is below or the axis is above. Top minus bottom. I'm just subtracting a negative, so I add it. Of course I add it, right? Moving the axis down, I increased it. If I move the axis up, well, this whole thing is some big monster 10. This thing is 4x or x cubed, and I have to subtract that away to get then this leftover. Top curve minus bottom curve, top curve minus bottom curve. And then you multiply all that out, do some fancy analytical integrals, and get 1168 over 21 pi. Okay, hopefully you can see all of these washers are stacked this way. So they're all dx. Every single one of these, I went from the axis to the outside curve and inside curve. Find big R, find little r, plug it in the formula, sum it up. X is in here, x limits, dx. All the same thing over and over again. Okay? But now I'm gonna take this same shape, okay? Except now I'm gonna revolve them around the y-axis. Let's go around this way. It's a different shape. Okay? I'm still gonna do the same procedure though. From my axis, I'm gonna go out. That's big R, that's little r. So that's big R, that's little r, and again, you're going to take this guy and you're going to revolve it. If you revolve this guy, you're going to get some big circle. Revolve this guy, you get some little circle. And so the washers are going to look like that. Okay, they're going to have a big radius of big R and a little radius of little r, and they're going to have thickness dy. The same thing. So the volume here is the summation. Now again, if I'm going to stack them vertically, I'm going to stack them all the way up to a y equals to 8. All of these were to 2 because they're all with x's. Now all these are going to be 0 to 8. That's how high I'm going to stack these things. Pi. All right, now what's big R? Well, I already did this for you. This is y equals 4x. So that means x equals y over 4. That's this curve. And this was y cubed, or excuse me, y equals x cubed. So that means this curve is x equals cube root of y. So in this case, this curve, this x value, the horizontal distance, is the cube root of y. So that's what big R is, right? This distance, cube root of y. So the cube root of y squared minus little r, which is this curve, y over 4 squared dy. I type all that in, and it looks like my notes say it's 128 over 15 pi for the volume. Okay, so same shape. Now let's move the axis over here. Same thing. Big R, little r. Hopefully you can see you're still making washers that are going to be stacked vertically. 0 to 8. Pi. That's big R. That's little r. Okay. This distance is the cube root. And then you, oh, wow, I didn't tell you how far I moved it. Let's make it x equals -4. Okay, so I moved it 4. So now this total distance is 4 plus the cube root of y. All right, the cube root of y plus 4 squared minus. Well, this distance is y over 4 plus another 4. So it's y over 4 plus another 4 squared dy. Again, every single one of these, I'm just doing this. I'm drawing big R and I'm drawing little r. I'm not going to draw these washers in there. If you want to draw them off to the side, you can. Again, this washer is going vertically. This one, there's big R, there's little r, and you sum up all those things. In this case, you can see that it's got a thickness of dx. All of these have a thickness of dy because the washers are going horizontally. Stacking them that way, dy, y limits with y's. You get a volume of 608 over 15 pi. Hopefully you can see I've increased the volume. Well, yeah, I'm taking this same area, instead of revolving it in a really close axis, I'm revolving it. It's going to be a way bigger, let's say it's a donut. I mean, it's not a donut, but let's say it is. This is a way bigger donut. Okay, so it's a way bigger volume. Okay, now what are we going to do next? Well, if I put the axis here, or I can put the axis here, I mean, putting it, ooh, let's put it over here now. Let's put it at x equals to 5. Again, big R, little r, every single time. There's big R, there's little r. My washers are still, again, if I look at this particular washer, it'd be something that looked like that. Subtracting that, it's still have thickness dy. Okay, we're still with y's. Accumulate from 0 to 8 pi. And then what's big R? Big R is this distance. This whole distance from here to here is 5. This distance is y over 4. So then it's 5 minus y over 4 squared. That's big R squared. Again, think about it for a second. Right curve minus left curve gives you this horizontal distance, as it always does. Right curve minus a negative, again, gave us that plus 4. Minus little r. Little r is this distance. The whole thing is 5. This distance is the cube root of y. So then that's 5 minus the cube root of y squared dy. And we get a volume of 472 over 15 pi. Okay, so you can't do anything else with washers. That's it. I did the 3 different examples with x's. That's all you can do. You can do the x-axis, you can move the x-axis down, or you can move it up. That's it. The curves can change, the intersections can change, but the theory doesn't change at all. Over here, I can have the y-axis, I can move it left, or I can move it right. Every single one of these examples, the theory says you are finding the volume of this 3-dimensional shape by summing up a bunch of washers, which is this formula, either dx or dy. If this is a dx or a dy, then the corresponding limits are also x or y, and then the values in here are x and y. The only thing I want to see on a test, because I think it's the most helpful thing, is draw a dotted line for your axis, draw one big R, one little r, write out the formula, make sure that these are x limits, x is in here, dx. You can double check to make sure that this gives you this distance and this gives you this distance. Make sure you squared them both, right? It's r squared minus r squared, not r minus r squared. Those are not the same thing. Don't mess that up, right? R squared minus r squared does not equal r minus r squared. And then if you have something like this, you're doing some horizontal axis, then you have to be with y's. Just look at your washers. You need to stack them vertically. So these are y limits, x is a function of y in here, and then dy. And again, just draw capital R, draw little r every time. Draw a picture, draw capital R and little r, and then write down the equation. Hopefully this is helpful for washers. Again, you got to put the discs and washers, and then the next video will be cylindrical shells. All 3 of those are going to be useful in different scenarios. I tried to give you all 6 scenarios for washers, and then with discs, I think I even gave you more than 6.